Welcome back, everybody. Let's get started with our next session. So our next session is on innovative software and hardware architectures for AI. My name is Volodymyr Kindratenko. I'm a research scientist at the National Center for Supercomputing Applications. And my research area is mostly in hardware architectures for this special purpose, hardware architectures and software that can take advantage of that, those special purpose architectures. So today we will have three presenters talking on sort of different aspects of innovation in the field of hardware and software for supporting AI research. And two of these presentations are from companies who make chips and tools and technologies and solutions around their chips to support AI. And one presentation will be from a supercomputing center which has deployed a system for training very large, very complex networks. And so with that, I would like to introduce our first presenter, Tom Gibbs from NVIDIA. Tom is currently responsible for strategy and implementation of programs to enable and promote developers to take full advantage of NVIDIA technologies. He has many, many years of experience in this area, starting with HPC and more recently supporting developments related to AI. And his expertise ranges from physics to aerospace to healthcare to life science to energy and financial services. So we were very, very happy to see Tom in today's session. And so Tom, please take it from here.
Sure, thank you, Vlad. So what I wanted to do is, and I understand I have about 15 to 20 minutes, is do an overview, kind of our perspective of the convergence of HPC and AI at NVIDIA, and leave you with some summaries on some of the software packages that we have that might be able to help bootstrap some of the researchers that are attending the session. So I'll start with the ubiquitous slide, which is the end of Moore's law, and I think one of the aspects of this which is missed is that the exponential growth in performance that we effectively got for free for about 15 to 20 years in HPC, as that is ending, it actually introduces a bit of a crisis, because the algorithms that are used for conventional modeling actually scale exponentially, typically n squared or n cubed. Some applications actually scale greater than n cubed, in which case, if I want to increase the scale of the model that I want to run, and I want to double it, I need 10 times the compute power. If I want to get 10 times the model size, I need 1,000 times the compute power. And that was actually happening for a number of years. But with that ending, it actually forces us as a community to take a hard look at the algorithms we're using and consider some alternatives. And I think serendipity has it that about the time Moore's law ending was introducing the big challenge to the HPC community, the deep neural net was effectively discovered, and we're putting it into practice in a number of very innovative ways. And I think we're just at the beginning of this innovative period, I think, in HPC, where essentially what we're doing is taking the knowledge we have of 40 years of numerical modeling and combining that with these new algorithmic approaches in AI, and it's opening up the ability to kind of continue the pursuit of grand challenges in areas from commercially, viable fusion. We talked about particle physics. Obviously fundamental to a number of us now is the response to COVID, and from maybe the smallest biological systems here on the planet, all the way to understanding dark matter, climate weather modeling. There are exemplars in each of these. I'm not going to go through all of that in this presentation, but there are, suffice it to say, exciting examples in each of these subdomains. To kind of characterize this, I want to say, what we've generally done with GPUs, probably I'd say from maybe 2010 to maybe the 20 teens, our primary focus was on accelerating the well-known simulation packages. In fact, the NCSA is home to one of the most important packages. In fact, it's really important for COVID research. That package is NAMD, and getting that code to scale and perform well on GPUs was a fundamental focus for us. With the help actually of some folks at NCSA and some other researchers in the US, we were just able to run, I believe, the largest molecular model ever run anywhere on Summit using this technology. It's about a 300 million atom simulation. The challenge there is that those models are really expensive. And so, as an example, that 300 million atom run took all of Summit. And if we wanted to run that model for a millisecond of simulation time, it would take an entire month. So getting all of Summit for an entire month is going to be a challenge. And so we need to look at new methods. We also need to look at the trade-off that, that as one of the ways that we improve the time to performance with various models in HPC is to use lower fidelity algorithms. So what's shown here in the molecular modeling case is classical force fields up to the closely coupled single, double, triple, where CCSDT is known as probably the most accurate modeling method. You typically can only apply that even on a supercomputer like Summit, or the Blue Waters machine at NCSA, or the upcoming machine that'll be rolling into NCSA here in the next few months. A couple of atoms, maybe 10 at the most. Hartree-Fock DFT models, maybe in the hundreds to 1,000. To get into the size of the models that we're talking about here that were just run with NAMD, we're using semi-empirical and classical force field models. And we have to make a trade-off here between accuracy and performance. And essentially what we're seeing with the introduction of AI into this space is the ability to kind of break those constraints and boundaries. So we can now try to address problems at scale that would have been unimaginable even in the era of Moore's Law, because the GPU is basically helping us track what you would have been able to get out of the CPUs during the era of Moore's Law, but that's still not enough. And so what's shown here are some dots on the chart for examples where we're seeing, multiple orders of magnitude improvement in performance and time to solution. To organize how these successes are occurring, because this is, I think we're kind of in the embryonic phase of this application method, and as Vlad noted, I've been doing HPC for quite a long time, and in fact, when I started, the Runge-Kutta technique was actually pretty novel, and there was actually quite a debate about the various Runge-Kutta methods that would be used and how they should be applied. And now I think most people using HPC don't even think about the Runge-Kutta. It's just another tool in the toolbox. I think we'll get to that point in AI, but since we're in the beginning now, what I wanted to do is just kind of organize what I'm seeing as a taxonomy. In modeling and simulation, what we're seeing is, and what I'll refer to as either is augmented or surrogate models. So on the far left, essentially what we see are research teams taking a piece of the computationally intensive part of the simulation out and replacing it with a neural net or a machine learned trained model. And that's done for two reasons. Either one, they want to dramatically speed the computation up, or be able to make it what I will call scale invariant. So if one part of the application scales by n cubed, and I can replace it with an inference engine, now maybe it scales linearly, and the performance improvement might be, as shown on the previous slide, hundreds or thousands of X. So I can now comprehend a much larger model, but still basically keep it within the confines of the simulation that has been built and tested for years. The other method is basically to use the simulation or experimental data, or the combination of the two, and train a surrogate model. And the surrogate model basically replaces the functionality of the entire simulation. And we'll kind of and usually that would then be replacing what currently is used as a reduced order model. So some workflows might use a DFT calculation for high accuracy, and then use various reduced order models as part of a workflow. And what we're seeing here is that the surrogate could either replace the CCSDT or DFT model as a surrogate, and you'd run many more of those than you would otherwise, and then you'd run the molecular dynamics simulation maybe in concert with that, or some flavor of the two. Probably one of the most exciting aspects of AI is that once an inference engine is trained, it typically only requires 8 bits to 16 bits to compute, and it's typically very efficient. So the performance improvement that you get with the inference in both accuracy and time to solution is also really efficient in terms of the amount of energy that it is required. So the ability to train a model on a supercomputer, get it running, actually use the inference engine maybe as part of the simulation workflow, and then take the same inference solution that you have and plug it into a in-the-loop, real-time embedded facility is not only possible, but we're deeply engaged in multiple projects that are pursuing this method. And the early experiments that we're seeing is it's essentially, and I think some of the folks in the neutrino space were discussing some of this, that you're getting a dramatic improvement in accuracy with these neural net methods, along with the fact that they're significantly faster. And we're seeing, in fact, what I want to talk about here with a couple of minutes is I want to go through some examples that are going to be tied to ITER. So the last example here is real time, and I'm going to come to this with the third in a series of examples around the ITER experiment. So one of the challenges with ITER is actually building the facility. And the challenge there is obviously, for I think most of the people on the call are pretty experienced scientists. They probably understand ITER, so I won't go into a lot of detail here. But you're basically taking and with electromagnetic forces creating a plasma that gets as hot essentially as the sun, and you're going to spin it in the tokamak and create atomic energy, which is very safe, far safer than fission. And the basic product that you need to power the experiment is water. And so as exciting as that is, you're still having to take this plasma, heat it to nearly as hot as the sun. There will be some collisions with the wall, so you can't avoid some collisions of this plasma. You're going to try to keep it confined. So there'll be some collisions, and that'll be the next example here. But in this case, you need to design the walls so that they're strong enough to withstand the occasional collision. This example actually gets into the challenges which I described before. So if you wanted to use, VASP or a typical density functional theory based atomic model, you could get the accuracy you need, but you couldn't run that model at scale, probably even on Summit for a hero run, to give you enough fidelity to actually do the modeling at the scale required to build ITER. So what was done at Sandia is they took a machine learned model. They used a spectral neighborhood analysis potential method, trained that. Actually, they modified it with the Gaussian method, some parts of the Gaussian method. So it's as a combined machine learning model. It's very physics based, so it's not a black box at all. And they were able to show that they got the accuracy of the DFT model, but we're able to run at the scale of the molecular dynamics model, which is LAMPS. This is a quick example of how that works. I'm not going to go into that in extraordinary detail, but essentially there are two machine learned potential models that can be used. They combined both of these and trained them. And essentially here we're able to decouple the molecular dynamics model from the modified SNAP, and combine the two back together and ended up with a hybrid, or what I've often called as an augmented model with lamps, and generate the performance curves which are shown here, where you're getting almost the DFT accuracy, and you're doing it at the level of scale and performance for molecular dynamics. And with that, we see a pathway to being able to do the kind of modeling that would be required to build ITER. Now, the next challenge is you've got to be able to keep the plasma under control. So you need to model how the plasma will work. Well, it turns out that the way these models are built, there's a couple of different ways you can model the plasma physics, and one of the more popular ways to do this, and one that has been part of the Exascale program, is XGC. The XGC model actually scales and runs at really pretty full scaling performance across all of Summit. It also ran across all of Titan. But one of the challenges is that one part of that calculation is referred to as collision, and it's essentially the way the particle and physics code that XGC represents essentially pushes the atomic matter for a certain period of time, and then calculates what the collision is if any of those the atomic matter escaped essentially the plasma confinement and would have collided with the tungsten walls, and if it does, then it models how that collision happens. Well, it turns out that there is now believed to be 40 species of tungsten in ITER, and the collision operator scales by n squared, where n is the number of species of tungsten. So this model, which currently runs on all of Summit, would have to scale at least a part of it by 160x. So what they were able to do, and this is work in progress right now, they just published a paper about a month ago, they were able to get a recurrent segmentation network trained at the 10 to the minus 5 level of accuracy required that they were able to do with the Fokker-Planck model. So very similar to what was done with lamps to actually build the ITER walls was done here to model the plasma. This inference engine is just being embedded into the main application, and we're doing the performance studies now. We believe we'll be probably in the 100,000x faster, and will be scale invariant effectively. So we should be able to handle this model and do it within the confines of the original software that was being built and is being built as part of the standard HPC environment. So this is another augmented simulation. The last example that I'll give will be on real-time control. So, and again, staying within the confines of ITER, that plasma, once it's spinning, as it were, you will get disruptions. And if you do, and those disruptions are significant enough, no matter how well the tungsten walls are designed, those disruptions can be dangerous to catastrophic to the experiment. Now, you don't get a nuclear disaster like 3 Mile Island if that happens, but you still have to shut the experiment down, and you don't have a commercially viable solution. So, the best-in-class support vector method that had been developed over maybe the last 10 years was able to get roughly in the high 80s in terms of the percentage of detection versus false alarm. So you've got the standard problem with a real-time control system. You want to detect that a negative event is going to happen, so you can react to it, but you don't want to react to a false alarm. So you've got this combination. The early research that was done here is called FRNN, for the Fusion Recurrent Neural Network. That work was able to demonstrate 95%, greater than 95% accuracy with a -5% false alarm rate, and was able to do that with a 60 millisecond lead time. So we're now in the ballpark of being able to control the plasma with a neural net enabled real-time control system. We don't believe that this is good. We know this isn't good enough. So we're probably going to need to get into the high 90s with probably, sub 1% false alarm rates. And we're actually doing some joint research. I think one of our researchers will be attending later this afternoon. Her name is Anima Anand Kumar, and her team has developed a technique which they refer to as higher order tensors, and that's being explored for some, along with some higher order elemental instrument readings that we could then use, and the team at Princeton could use to actually implement the real-time control. This project is actually underway right now at the D3 experimental facility in General Atomics in San Diego. So those are some examples of how researchers are applying these methods. What I did want to kind of close with is, what is NVIDIA doing to help besides build hardware that runs really fast? Which we're doing, and we're really pretty excited about that. We just introduced a new product family, the A40, here last week at GTC. We're really excited about that, and I believe that NCSA is going to be getting their new machine. Will have a few of those, along with the A100 that was introduced earlier this year. But this is software packages, and essentially what you see from NVIDIA are packages that we're pulling together that are combined not only higher order abstractions like TensorFlow and NumPy and some of the things you might be familiar with, but they're fully organized against subdomain problems. So Clara is built for healthcare, and I'll give a quick example of what's in Clara. Drive is for autonomous driving. Isaac is for robotics. Jarvis is for interactive speech recognition. So these are pre-built packages in the open source domain that researchers can pull down, so you don't have to start from scratch. And what's been shown over and over again is that we can start with these higher level packages that are basically off the shelf, and through active learning rapidly retrain them and apply them to your specific science problem. Clara includes elements of genomics, structural design, docking, simulation, imaging, all in one combined package. These are all containerized. So specific simulation packages, like the one that was built at NCSA, NAMD, is available as a container as a part of this package. We've got a GPU optimized docking routine, AutoDock, part of the package. The ability to do cryo-electron microscopy, CryoSpark, the optimized version of that, again available in a containerized package. So essentially what we're trying to do is simplify the time to ramp. So historically in HPC, if you were going to start, you started from scratch. It was maybe somebody else's a little bit of code, and then you got started. And here we're basically providing I want to say loosely integrated package of highly integrated software that you can combine to get started in your research. And then at a slightly lower level, we have Rapids, which is an integrated toolkit of machine learning utilities that are all built on top of Apache Arrow. So commonly used utilities like Dask, NumPy, and then the frameworks that you're familiar with, like PyTorch and TensorFlow and whatnot, are all optimized. So, all the CUDA low-level software work has been done, and you can pull these off the shelf and put them into practice immediately. What we're seeing in the scientific domains is that experiments like the Large Hadron Collider at CERN are building utilities. One of them is Uproot. They're in the process of expanding that with a more sophisticated utility they call Awkward Array, which will get the data out of the root package, which is the common data organization and framework that's used at CERN, pull it up so that you can then put it into the Arrow framework. Once it's there, you can then apply all of these utilities from Rapids, and you're basically doing data science on the GPUs at speed, and your ramp time is like hours. And we've had some examples from some NSF programs where researchers did exactly that. And it's really exciting in terms of the ability to implement and get better time to science with much less effort. And with that, I think I'm about out of time, Vlad. So
yeah, that's right.
I'll wrap up.
Okay, well, thank you very much, Tom. Yeah, I think unfortunately we don't have time for questions, but maybe we can have these questions asked at some later time. So let's move on to the next presenter. Our next presenter is Nicholas Fraser, who is a senior research scientist at Xilinx Research Labs in Dublin, Ireland. And his main area of research is in quantized neural networks and also custom computing architectures for neural network inferences on FPGAs. And so, Nicholas, please take it from there.
Hi, thanks for having me. Let me know when you can see my screen.
Yeah, we see it.
Great. Okay. Thanks for the introduction. I'm Nicholas Fraser, researcher at Xilinx Research Labs. Sorry. And I'm just here to talk to you about the research that my team is doing on quantized neural network inference on FPGAs under two sort of project names, and there's FIN and Logic Nets. So firstly, I'll just kind of introduce Xilinx Research Labs, and maybe there's some people here who are interested in that and interested in collaborating. We're very interested in collaborating. Then I'll quickly follow up with, a little bit of introduction into FPGAs. I think that might be helpful. I find that a lot of communities, and I'm not sure how exposed this community is to FPGAs, but people seem to talk about FPGAs in terms of magic, but they're not, and they're real devices, and they're useful for some things and not for others. And maybe explaining them helps you to identify what they're useful for. Then I'm going to talk about a little bit of neural network quantization and FIN, which is one of the projects from my team, and follow up with a bit of, let's say, bleeding edge research from our group, a project called Logic Nets, which is a co-design technique for neural networks and hardware accelerators for inference. Anyway, so very quickly, Research Labs in Dublin was established about 14 years ago. It's now at 7 full-time researchers plus interns. We often have kind of one intern per researcher. So if you're on the call and you find something that I'm talking about to be interesting and you think you want to work on that, please contact us, because we're always looking for interns, and we tend to sort of have a one intern per researcher kind of ratio. So actually you get a lot of attention from the researcher that you're working with. And the research that we do is in applications and architectures. So identifying applications where we can use Xilinx devices, and then how you actually design a solution to run on Xilinx devices. And I'll talk a bit more about that. So firstly, let's go right back to the start. Let's talk about what are FPGAs. So originally, FPGAs were a specific type of semiconductor device that contains basically a matrix of configurable logic blocks and a flexible programmable interconnect. Okay, so probably for a lot of people on the call, that wasn't very useful. So configurable logic blocks, let's think about this in terms of the main sort of piece of hardware there is a 6-input, 1-output lookup table. So this is something that's capable of performing any 6-input logic function. So any 6-input logic function you can think of is able of doing the whole truth table of the whole space of possible 6 binary input logic functions. Okay, so then we have a flexible interconnect, flexible programmable interconnect. So now we've got these logic blocks. We can program them to do any logic function that we want. Now we can decide how to actually connect them together. And from that, we can essentially do something like design a circuit on a device. So a lot of people think about designing solutions for FPGAs as more like circuit design than it is like building software. Now that was originally, and things have moved on a lot since then. So on newer FPGAs, you also have some hardened blocks to do common pieces of work that people would often do. So for example, on modern FPGAs, you have thousands of what we call DSP blocks, which are basically doing like little, multiply, accumulate blocks, but then you still have this flexible programmable interconnect to basically connect them together in any way that you want. We have hundreds of megabits of distributed SRAM, which are often called BRAMs, and we have things like ARM processors. Because back in the day, a lot of people would sort of design FPGAs and design an accelerator for the compute-intensive part that they were interested in accelerating. Then they would implement in some other of the logic resources. They would implement a processor to actually, parse data and control that accelerator. Now we do things like, okay, let's just put an ARM processor in there so everybody's familiar with it. They can run Linux, they can do that sort of stuff. So the main takeaway that I want you to get from this bit is that when you're programming an FPGA, you're designing a circuit, and an FPGA can be programmed to become any circuit. And so actually, often and traditionally, the tools that you're using are the same tools that people would actually use when they're designing a silicon circuit, right? And so actually, this is a big part of, back in the day, FPGAs, one of their uses were, people were investing lots of money to design a microchip. And actually, they could buy an FPGA and they could implement that circuit on the FPGA and they could test it before they actually went out and stamped out, millions of these devices and spend those sorts of costs. Okay, so now I want to talk to you about the first project, which is custom neural network inference with Fin. And I see we are running a little bit late, so I'll try to be as quick as possible. And apologies if I go too fast for some bits. So we just talked about, for example, that programming an FPGA is like building a circuit. So we can actually build, if we want to do something like accelerate deep neural networks, we can actually come up with a whole bunch of different alternatives. We can build whatever circuit that we want, depending on what sort of objectives that we want to achieve. So for example, I'm just sort of drawing these on a spectrum here, and I'll come back to this spectrum at various points during the presentation. So on the left, maybe you have something that is not very efficient, not very specialized, but is broad and kind of works for all of your applications. So an example could be, that you instantiate a basic processor like the one that's CPU that's sitting in your laptop. And then you use all of those DSP blocks and all of those logic resources on the FPGA to build a really big matrix multiplier. And then basically all you do is you overload all of your matrix multiplier operations to call your big matrix multiplier, and you run everything else on your regular CPU. That could be a way to use an FPGA. It's probably not going to be the fastest, but you could take some off-the-shelf software and you could run it. On the right end of the spectrum, we have something that's a bit more specialized, right? So maybe we're designing the neural network and we're designing the accelerator at the same time. And I'll talk a bit about those. So first, I want to go back to quantization and why it's important. So if we look at this very, very simple neural network, it's very simple, but actually it has probably the main core operators that we're interested in actually accelerating, which is a dot product. Now, on a traditional neural network, you would have floating point weights, floating point activations, everything's floating point. And this is really, really great because it's a very good number representation system with very good error characteristics, but it's quite energy intensive. So if you actually go and you have a neural network that you've trained and you want to deploy in some kind of constrained environment, floating point might hold you back in some way, right? So floating point arithmetic is basically inefficient. It's using energy, and somewhere this is also going to limit your performance and possibly other metrics. Okay, so alternatively, we could do integer arithmetic with a quantized neural network. So this is the same one, but actually we've quantized all of those weights and activations that we saw earlier. And let's have a look at, when it comes to FPGAs at least, what are these sort of accuracy and performance implications of doing that. Okay, so if we look at a particular Xilinx FPGA device here, and we compare the amount of operations that you could do per second, going all the way from, let's say, a binary neural network, so binary weights and activations, to 32-bit floating point, there's about a 200x difference in performance, right? So if you're willing to give up, let's say, floating point weights and activations, what you get back for that is you can maybe have a neural network that has 200 times more actual operations within it. And there's a whole spectrum in between, because again, we can use these flexible logic resources to build any sort of multiplier that we want. There's no reason why you can't have a 7-bit multiplier if you want one. All right. Secondly, when it comes to memory, right? So if we're willing to actually quantize our weights to be, 32x smaller, right? Well, we can fit 32x times more weights on chip. Maybe we can fit all of our weights on chip and we don't have to go back to memory anymore, right? So this is great for efficiency, right? Actually, one of the big performance bottlenecks that you hit are actually memory bottlenecks. But let's talk about what this does to accuracy. Okay, so here is an example of a network that I've trained. This is an object detection task, and these are YOLO-like networks. And I've taken 4 topologies here. I've trained them with different precisions for the weights and activations. And I'll just kind of rush through this a little bit because we're a bit behind time. So basically, here's the 4 topologies, right? So Tiny YOLO, YOLO 9000, and YOLO version 2. And on the y-axis in this graph, we have mean average precision. So this is the accuracy metric that's often used for object detection. And on the x-axis, we have compute cost. So this is a relative measure of how much of an FPGA's resources we would use if we wanted to implement this network at a constant frame rate. So ideally, where we'd like to be is we'd actually like to be in the top left-hand corner of this graph. We'd like to have as high accuracy as possible, and we'd like to use as little of the FPGA resources as possible, right? And so what happens if you actually look at this space, comparing multiple architectures and multiple different precisions? We actually see, right, if you look at 2 points, say, and you're capped at compute cost, let's say you have an FPGA of a certain size, you can't go above that for whatever reason. Here are 2 different examples of networks that you could implement. And by changing topology and actually going to lower bit depth, significantly lower, right, you can get a 15% accuracy increase for basically similar hardware cost. Another point of interest might be this one. So here we're getting an 8% increase in accuracy for 5x reduction in hardware cost. And here hardware cost translates into performance. So you could run this 5 times faster, or you could use 5x less of the FPGA resources. You could use a smaller FPGA, or you could use other parts of the FPGA to do something else, right? And what these define when you go off and you look at it is you get a bunch of Pareto optimal solutions, right? So these are solutions that are optimal in some metric. So if you want to go for full accuracy, based on these results for these specific example, it doesn't look like there's any reason to actually use floating point. The 8-bit networks get the same accuracy, but for reduced resources. But some of the other points of interest are the trade-off points, right? Basically, all the 1-bit weight, 3-bit weight activation networks are shown here. And even one of the 1-bit weight, 8-bit activation networks is shown here. So Finn, this tool I'm about to describe helps you sort of explore this space. Okay, so before we go any further, let's look at how most hardware accelerators work, right? So usually you have a network like you have in the top right, and you have some hardware like you have in the bottom right, a matrix of processing engines. And what you do is you take every layer of your neural network and you sort of schedule it across those processing engines, okay? Now this is great, again, because it's flexible, but it suffers from some one-size-fits-all problems. What if those layers are not configured in a particular way that means that they can be run efficiently on that matrix of processing engines in those dimensions? right? So this is kind of where we step in with Fin. So what we just previously saw is something like you would get from Xilinx's Vitis AI tools. It's what you get with most, most other accelerators of this type. And Fin is a bit more customized, right? So it's actually a custom streaming architecture that matches the topology of our neural network. And I'll quickly explain what that means, right? So what we do for our accelerator is we take the actual topology of the neural network, we duplicate that topology in the programmable logic of the FPGA, in the FPGA's resources. We tailor it so that each layer has the amount of FPGA resources that it needs to maintain a balanced pipeline. And then we essentially push the data through, right? And this allows us to be extremely efficient in the way that we use the FPGA and achieve very high throughput and very low latency, right? And here are some quick examples of things that you can do. So on a device that's consuming 20 watts of power, you can do highly accurate inference of MNIST, something like above 10 million frames per second, sub 1 microsecond latency. Similarly, if you want to do some image classification on Cypher 10, maybe you can do 3K FPS at around 1 millisecond of latency. And similarly, on a sort of server card, you can use, you can do inference of ResNet 50 at kind of 2 milliseconds of latency mark, okay? So what we're trying to do here in Fin, right, in this project is we're trying to give people the ability to design at the same time algorithms and architectures that run on FPGAs that sort of match each other. So achieve efficient neural network topologies along with hardware that allows you to efficiently utilize the FPGA, right? And this is all open source, and yeah, you can go check it out. Now, I see Vladimir, you can cut in when I'm out of time, but so just quickly talk about some of the components of this. So this is the full Fin stack, and at the first step we have a PyTorch library called Brevitas, which is basically a set of PyTorch layers with extra parameters that let you define your quantization scheme. And actually it has the ability to learn some of those quantization parameters with backpropagation, which I think is pretty cool. Next, we have the Fin compiler, which takes a Brevitas-like network and converts it into a Fin accelerator. And it provides a whole bunch of transformations to make sure that process is as efficient as possible. And then this is actually a separate project in its own right. We do deployment with Pink, which is a Python on Zinc, which is a particular type of Xilinx FPGA device, which means that we can interface with this accelerator using Python and NumPy and things like that. And again, as I said, this is all open source, and we have somewhat of a community that's growing that are using this. And if this interests you, please check it out and be in touch. So lastly, if I have a couple more minutes, I'll just talk about
just a couple of more minutes, no more than that.
Okay, I'll just quickly talk about some other work that we're doing called Logic Nets, and maybe I'll give the very brief version. So let's forget about things like ImageNet. Let's talk about extreme throughput applications. So we're talking about doing things like processing the sensor data that's coming from your particle collider. We're talking about doing things like malware detection on your network infrastructure. Okay, where can you get hardware that can sort of meet the constraints of these sorts of applications, where you have extreme throughput requirements, very low latency requirements, things like that? And we've designed Logic Nets to basically address this. This is a co-design method of designing neural networks to support, to enable extreme throughput applications. So we can achieve hundreds of millions of inferences per second at sub-microsecond latency. And this goes on the sort of extremely specialized accelerator on the right of our spectrum. So at a glance, basically what you have to do is, given a data set, in PyTorch, we provide you with some layers that have some constraints in place. These are quantization constraints and sparsity constraints. And then you can go ahead and train your network, after which you can convert that network directly into a fully spatialized circuit. So fully spatialized means that basically you can process an input for your neural network as fast as you can clock your chip. Okay, so this is hundreds of millions of frames per second, samples per second. So here's some quick results for malware detection, for checking network packets and checking if they're suspicious or not. We can achieve something like hundreds of millions of samples per second at the sort of 10 nanoseconds of latency or lower for reasonably high accuracy. And if you want to hear more about it, there's some links for a longer sort of YouTube video about it and our FPL paper. And that's it for me. So thanks so much for having me.
Okay, well, thank you. Let's move on to our next presenter. So our next presenter is Dr. Sergiu Sanielevici, who is the director of user support for scientific applications at the Pittsburgh Supercomputing Center. So he is a copy on two recent awards to build large-scale systems. So Bridges 2 and sort of what's more relevant to this presentation is the Neocortex system. That is to deliver a system for deep learning, for training very large complex networks. Dr. Sanielevici obtained his PhD in quantum field theory at McGill University in Montreal, and he has been with Pittsburgh Supercomputing Center since 1995, where his main responsibility is to help computational science community to become productive on this high-scale systems.
Okay. Thank you, Vlad. Can you hear me?
Yes, we can hear you.
Okay, so I'll just give you the punchline, which is the proof is in the pudding. So what NSF basically wants us to do, the reason they gave this award, is that they want us to work with the research community, very broadly defined in principle, and to basically see what this thing is good for. So they give us, 5 years to try to explore in conjunction, and that's very important. We have a research partnership with Cerebras, who are of course, the inventors and manufacturer of the CS1 system, and also with Hewlett-Packard Enterprise. And the three of us are to work with the research community to figure out what CS1 and maybe future generations can actually do in terms of accelerating machine learning. So here are the project goals. We are about to deploy the system, and as I'll describe the system briefly. And then to work with the national open science community to accelerate AI training and fit it into all kinds of workflows. Vlad also mentioned Bridges 2, and as I'll say, Neocortex will be complementing Bridges 2. And in Bridges 2, of course, we are closely collaborating with NVIDIA, and we're doing the kind of things that Tom was talking about. So what we're curious about is the complementarity and the how one approach can complement the other. And so again, I'll go very quickly through these things, and at the end, I'll give you the email address that you can reach us at with any questions, and perhaps to explore, to talk and see if your application can take advantage, at least at some point, in what we're doing. But again, Tom showed this. This is the revolution that has happened in machine learning, which of course is way beyond what Moore's law can deliver. And Here are some illustrations of the growth actually is specifically in terms of parameters that have to be trained, which seems to be really exponential. So I think even the GPT-3 is already exceeded by GPT-4 by a large amount. So we need a lot of compute. And of course, as you know, training in machine learning is not a linear process, but it's a very iterative, painful thing. You have to go through, as we've seen, potentially billions of parameters that you have to try. You may want to try models. So it's very compute consuming. And here are some quotes from Yannick LeCun, whom you all know as one of the godfathers of machine learning, arguing why, how if, that the growth in hardware is actually very symbiotic and integrated into the evolution of AI research, both in theory and in the ability to produce results. So briefly, what Cerebras, for example, was looking at is they were trying to look at properties of the right compute for deep learning. So we need massive compute. There's a lot of sparse linear algebra. It has to be flexible, and that's, I guess, also what FPGAs aim to achieve. There are memory requirements, so we need large high bandwidth memory tightly coupled with compute. And we don't want utilization to depend on batch size. And then there needs to be a fabric that is high bandwidth, low latency, and fully configurable. So that is what we aim to bring to the academic research community, Neocortex. So Neocortex, again, tries to achieve these goals. It is offered, of course, at no cost. Eventually, it'll become part of the systems that are allocated by Exceed or whatever program the National Science Foundation might set up to succeed Exceed when it ends in the fall of 2022. But non-academic people can, of course, also contact us, and we can give them access as well. So we called it Neocortex because it's the newest and smartest part of our brain. What it'll be is, so there will be 2 CS1 servers and front-ended by an HPE Superdome Flex. And it will be federated with Bridges 2, which is a capacity system, lots of storage, lots of compute power, including both in terms of on CPUs and on GPUs. And so it'll enable a whole ecosystem of applications, both in terms of HPC and in terms of AI. Again, I sent the slides to Vlad, so he will share them. So, and also we have quite a few other talks on this topic. So, and you can talk to us about the details. But so, again, I apologize for going through quickly. But so the system was specifically designed for demanding deep learning training, complementary projects on Bridges 2. Again, we're very interested in complementing simulations that are large-scale simulations on Bridges 2, and also surrogate model training, again, getting back to what Tom was saying. So here are some models that fit the bill in principle, but of course the proof is in the pudding, as I said. This is kind of the block diagram of the system. So we have these 2 CS1 wafer scale engine systems. They're front-ended by a 32 processor Superdome Flex, and then they go over into the Bridges 2 system. So if you haven't seen it before, this is the CS1 server, the wafer scale engine, which is the biggest processor by area built to date. And there are some deployments, as you may know. Argonne has had one since last year. Livermore has one. I think GlaxoSmithKline has a CS1. So here are again the statistics of the wafer scale engine, the compute part of it. So it's fully programmable sparse linear algebra cores, optimized for tensor operations. The memory is integrated with the compute, which should be good because all memory is local, can support small batches. And no communication bottlenecks enables training models in parallel. So small batches you can train at high utilization. Normally, and this will be the first time actually that this is a tradition at PSC, that we always try to be serial number one in a certain sense. This is going to be the first time that we are going to put together two CS1s front-ended by a Superdome Flex. Normally, CS1 deployments are front-ended by a conventional CPU cluster. So this should be advantageous in terms of both preparing the data and then doing complementary data and also doing, quite considerable graph analytics, even if it doesn't use the CS1. So yeah, that's what we say here. Software stack, yeah, you can come with your say a TensorFlow. You can think of it in terms of TensorFlow Evaluate, and there are actually containers where even before you get to the system, you can use CPU's container that is provided in order to do the compilation and simulate how it's going to run on the fabric. So that will always be the case, that you'll be able to use to just bring your model from a standard popular framework. But there is also a low-level programmable C++ interface that folks can use. So this is essentially how it works. The framework is matched onto a kernel graph, which is then planned onto an execution plan onto the wafer. And the thing that I would really just like to point out is that we are in the process of planning for the early user program, which we hope to get to in November, December timeframe. This is the initiation of a partnership between the Neocortex team and the research community. Early user program is kind of a reserved term in NSF acquisitions. It is a 30-day period that we actually have to have users as part of the acquisition, but that's only the beginning. And we're talking to groups that, after somebody's been on for 30 days, that's just the beginning. They'll stay on for conceivably the next few years. So, certainly in the beginning, but ongoing, participating groups will receive one-on-one assistance from PSC and Cerebras. So what we've done so far is we have used an easy chair, like for a conference, to invite proposals. In a 1-month period, we've received 42 proposals in a wide variety of research areas. And at the moment, we're engaged in talking to these groups to kind of see what can be done in the first 30 days and then what should be done later. So, and then before we, as we build the system, which will be, again, in a month or so, people can already get started, as I said, by compiling on, say, on bridges or regular PSC supercomputer. So target, the project formally started in June. We hope to, there's been some delays because of COVID, but we want to install the system in November and then do the early user program, let's say in December. These are target timelines. And then we will have a couple of years to really experiment, and we are committed to making it available as part of the National Science Foundation program, but we have 2 or 3 years to do that. So this is the really important slide here, which is to get in touch with us. You go to the website, and there's actually an email address, neocortex@psc.edu, and that's where you'll find us. So welcome all questions there. And in particular, we can then explore with anyone how we could work together. So this is the summary, and again, the punchline is the website, and that's it. Thank you very much.
Okay, thank you very much, Sergiu. All right, so I think that concludes our session on innovative hardware and software for AI, and we can move on to the next session.
Thank you.